All right, let's get started. So today we're talking about rational and irrational numbers and the kinds of numbers that we find in our number system that we haven't explored too much yet this year. So we'll get into that in just a minute. But first of all, let's review a couple of concepts that we have seen in the last week or so, just to make sure that we don't forget them. So the first question is this function linear or nonlinear? And if you'll remember, we can tell if it's linear if it has a constant rate of change in the x direction and in the y direction, meaning that it would just have a linear slope. So let's look in the y direction. The change in y to go from -2 to -1 would be a +1. To go from -1 up to 0, that would be another +1. And to go from 0 to 1, another +1. So in the y direction, as we move up this set of ordered pairs, we're jumping up by 1. How about in the x direction? So to go from -10 to -5, that would be an increase of 5. To go from 5 to 0, another increase of 5. And from 0 to 5, that would be another increase of 5. So yes, it's going up by a constant rate. And if we were actually to put down the slope, based on what we've just seen, the slope of this line would be up 1 and over 5. So it would have a 1/5 slope. So that's kind of how you do that. So that would make it a linear function in this case. All right, how about over here? Graph the function and label it. Okay, so cups of milk, 1, and pancakes, 6. So over 1, up 1, 2, 3, 4, 5, 6. So it takes 1 cup of milk to make 6 pancakes. Oh, I can see we got a problem here. If you notice, the graph has not been labeled, and our numbers are going to get really big really quick. So I'm going to need to alter my graph a little bit. I know the highest I'm going to have to go on the y-axis is 24. So let's see how many lines we have to work with. 1, 2, 3, 4, 5, 6, 7, 8. So if we divide 24 by 8, we can make each line amount to 3. So let's do that. 3, 6, 9, 12, 15, 18, 21, 24. So as you can see, I got to decide how the scale on my graph would go based on how many numbers I needed to come up with and how many boxes I had to work with. Now, how about across the bottom? We know that cups of milk only goes from 1 to 4. So let's look 1, 2, 3, 4, 5, 6. That's kind of a tough number to divide. So let's just go ahead and say each box is 1. So 1 cup of milk. Next one would be 2 cups of milk. The next one, 3 cups of milk, and 4 cups of milk. And then if we decided to make more pancakes, we could change the graph a little bit more. So let's graph our information. 1 cup of milk, 6 pancakes. 2 cups of milk, 12 pancakes. 3 cups of milk, 18 pancakes. 4 cups of milk, 24 pancakes. So there's our graph. And now the question is the domain discrete or continuous? And since we can count pancakes and we can count cups of milk, because we're doing it a cup at a time, this would be a discrete domain. So there we go with that. Now this last one, you'll recall that when we started using function notation, this just told us that we could now evaluate this function by putting this number in for x each time and seeing what it equals. So we've got 2 times -3 minus 4. So that would be -6 minus 4, which is -10. So the first one would be -10. The second one, we're going to plug in the number 3. So 2 times 3 this time would be 6, and 6 minus 4 would equal 2. A big difference when you change the sign like that. And then the last one, 2 times 0. 2 times 0 minus 4 is equal to negative 4. So there's our three numbers when we plug in these inputs into this function, and these are our three output values. Okay, so let's get on to today's lesson. So we've handed you out a set of guided notes. And here's our title page. And so we're going to kind of build our understanding of this diagram here as we go. So if you look at your notes, you'll notice that the first one is identifying types of numbers. And the first set of numbers that we learn about as we begin to grow up and learn about math in the real world is called natural numbers. This is basically the counting numbers starting at 1, 2, 3, 4, 5. And so perhaps somebody a long time ago, when they were trying to count things or keep track of who had the most cows or goats or whatever the case might be, started coming up with some numbers that sounded natural to them. So we call them natural numbers because they're just counting. All right. Well, then somebody said, well, if we get big enough, we're going to run out of numbers, so we're going to need to come up with another number that's going to help us write bigger numbers. So they came up with this digit called 0 and added it to the list. And they thought, okay, these are all the counting numbers and 0. So we've got a whole list of numbers now. We've got all the numbers we need, so they call them whole numbers. But someone else said, well, that's really not all the numbers that we need too, because what if we go in this direction? What if we go below 0? That's possible, isn't it? A lot of things like temperature or digging holes in the ground would be below 0. So we had to come up with another set of numbers called the integers, which stands for all the positive and the negative whole numbers, including 0. So as you can see, we're building this set of numbers, and we've added integers to our list. And as we keep adding new circles like the integers now, you'll notice that all the numbers that we talked about before we got to integers, like the natural and the whole numbers, are inside of that integer circle, meaning that all integers or all natural numbers, all whole numbers are also considered integers. But there are some integers that are outside of those circles that are not whole numbers or natural numbers, and these would be the negative integers that we're talking about. Okay, we have a couple more words up here we got to talk about. What do we mean by rational numbers? Okay, so the numbers that end or have a repeating pattern, and we're talking about decimals, anything that can be written as a fraction. So these are just some general definitions for a rational number. So there are numbers like the ones we talked about, the natural, whole, and integers that can be written as a fraction, but there's also numbers in between them, in between those counting numbers, like 1/2, 23.8, 12.1212, or even repeating decimals, 0.33333. These are all numbers that are useful, that are not necessarily accounting numbers, so we had to add another number category to take into account all of these numbers that are not considered counting numbers. And those were called rational numbers, and they include all of the previous sets, the natural, the whole, the integers, because all of these numbers could be written as a fraction as well. All right, let's keep going. There's one more set of numbers that we haven't mentioned yet, and that is the irrational numbers. These are numbers that represent a non-repeating or non-ending decimal. So we found out that when someone calculated the number pi, or when they took the square root of something like 19 or 7 or 5, something that's not a perfect square, they ended up with a decimal that just keeps going out forever and ever and never ends or never repeats. There's no pattern to its decimal. So because it's kind of crazy like that, they decided that and because they can't write it as a a real fraction, they just started calling it irrational, which kind of sounds like what people are when they're behaving badly, right? They're being irrational. Okay, so let's take a look and see how much we've learned about these sets. So identify each number as rational or irrational. So this first number is a decimal, so that would be considered a rational number. Second number, it has a decimal, and does it repeat is the question. 0.10101001. So it has a non-repeating pattern. So this pattern keeps changing as you go out. So really, that's kind of an irrational number. How about this next one? 0.3131113331. All right, so there's another pattern that is not decipherable, so that would be considered irrational. If I take the square root of 7 on my calculator, it ends up being a decimal that doesn't terminate or repeat, and you can try this on your calculator if you want. In fact, let's grab a calculator and just check one out. So we get a calculator, and we're going to go the square root of 7. So square root of 7, square root is 2.6457113. Do you see how that decimal just goes out forever, never repeats or terminates? That's why this is an irrational number. How about the square root of 52? Let's get that calculator again and see what it says. So 52 square root. Oh, it's another irrational number. How about 49? Let's check that one out. And then we won't do them all on the calculator, but this way you can at least see what some of them are like. So the square root of 49 is 7. Oh, so that's not a decimal that doesn't terminate or repeat. It does terminate. So this is considered to be a rational number. This next number, 0.343434, is a repeating decimal. So that's considered rational. Another repeating decimal, that's considered rational. This next one terminates, so that would be considered a rational number. The square root of 16 is just 4, so that would also be a rational number. The square root of 3, we better get our calculator and show you what happens when we do the square root of 3. We get this other number that looks like, kind of like pi. It's a number that goes on forever and never terminates and repeats. So the square root of 3 would be irrational. The square root of 36 would be 6, so that makes it a rational number. So there's just an example of some rational versus irrational numbers. Okay, now what if we wanted to convert a decimal to a fraction, just to kind of compare it? Well, if we look at the 0.34, we notice that this is in the hundredths column. So to turn this into a fraction, we would just go 34 over 100. And then we would simplify it. And so that would, just going right off the top of my head, that would simplify to be 17/50ths. And that's as far as that'll simplify. How about this next one? Well, that's a negative number, but we would also write the digits 5, 7, 8. And then the bottom of the fraction, because the 8 is in the thousandths column, the bottom number is going to be 1,000. Now the question is, can you simplify that? And if you put that on your calculator and just do 5, 7, 8, ABC, 1,000, it does simplify. And it's hard for me to show our calculator display on this screen right here, so I'm going to count on you to do that at your desk. So this simplifies to be 289 over 500. And we got to remember that's negative, though, because it was negative to begin with. So a negative 289 500ths. Okay, so converting a decimal to a fraction. Well, here's another question that we need to address. How do we convert a repeating decimal to a fraction? Is that even possible? Well, the answer is yes. So, for example, if we have the repeating decimal 0.3333, and it just goes on forever and ever. So we are not going to write them out forever. We're going to just get a few of them, like so in this case, 4 3s, and then just put some dot 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 to represent the repeating decimal. All right, so now we're going to set that equal to x, just some variable x, and then we're going to multiply both sides of our equation by 10. So we'll end up with 10x equals 3.3333. So that basically moves the decimal over one place. All right, now we're going to subtract the first decimal, subtract this decimal from this decimal. And we are showing that down here. So when we do that, all the 0.333s out here disappear, leaving us with what? Just a 3. 3 minus 0 is 3. So, and then 10x minus 1x is 9x. So then when I divide both sides of this equation by 9, I end up with x equals 3 over 9, which is 1/3. So 1/3 is actually the fraction equivalent of the repeating decimal 0.333333. And you can convert these this way, but there are some shortcuts that we will get into as time goes on. Oh, for example, like look at this one. We've got 1.2525 dot 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 dot. So we know we have 2 digits that repeat. And so our little shortcut method for converting that into a decimal is to write the 2 digits that repeat. And instead of writing that over 100, because this is a repeating decimal, we're going to write it over a 9 and a 9. So 2 9s, one less than 100. So you take however many digits that repeat and put that many 9s under it to create your fraction. So in this next one, we have 12, and the digits that repeat are 361. And since there's 3 of them, we're going to put 3 9s underneath this 361. And there, now we have a fraction that goes with this repeating decimal. And sometimes you might be able to simplify these down a little bit. Sometimes you won't. Okay, now what if I want to order some fractions from least to greatest? Well, sometimes I like to just divide them out and find out what they are as a decimal. Or in this case, let's look at it. We have one of each of these. So what's bigger, a third, an eighth, or a sixth? Well, we know that a third's bigger. So that means that the 1/8 is going to be the smallest. So if I order these from least to greatest, I would have 1/8, 1/6, and 1/3. So that's ordering them from least to greatest. And that works especially well when you have a 1 on top, because you can compare those quite easily. So on Alex, you might see something like this. Can this be written as a fraction? So if you look at the number, yes, that could be written as 74 hundredths. And this is a terminating decimal, so we know that it could easily be written as a fraction. And yes, it's a terminating decimal. Okay, this is a repeating decimal. And so we just learned that yes, you can write repeating decimals as a fraction. And so we put yes, this is a repeating decimal. So on Alex, it'll give you a couple of problems like that. All right, so we're also going to see some problems that ask us to kind of reconstruct this number chart. And then here's the number chart we had on earlier in the notes, but this one that we're left with is missing some of the circles here. So let's see if we can figure out what's missing here. We know that the outside circle is going to be, out here is going to be the real numbers or irrational numbers. Well, they don't even give us that choice, do they? What's the next circle inside of the outside? Well, we have rational. So we're going to pull that rational down. We're going to call this rational. Oh, we're going to call, where's our rational numbers at? Oh, never mind. what we're going to do, yeah, we will, okay. So what we're going to do is just kind of put the words on there. Normally on Alex, you'll be able to drag them over there. But, so we're going to go this, and this is going to be rational numbers will be the outside circle right there. So the next circle in from that would be integers, right? Integers. All right, so now we've got that figured out. And trying to make them a little bigger so we can read them better. So we got rationals and integers. And then outside of that would be irrational. So now what we want to do is drag these over and one at a time into the set that they would belong to. Let's see if they'll let us drag it. Nope, they won't. So what would be the integers here? And on Alex, it'll work a little bit better, but for our integers that are in the list here, the integers in that group above would be 18, 11, and negative 27, which means that the rational numbers would be these three numbers as well as those other numbers that don't fall into this set. So what are we talking about here? We'll just highlight them here. The rational numbers would be the 1/11th and the 0.4 because they are strictly fractions and they're not integers. We do know that the other ones could also be rational numbers because they can be written as a fraction like 18/1. But 0.4 repeating and 1/11th are just rationals. They are not integers. Okay, so what we're doing is an Alex assignment number 30 called rational and irrational numbers. So you get to practice discovering these numbers. Feel free to go back and look at your study guide if you get stuck on something, or ask a teacher if you need a little help. Thank you very much.